Okay, chemical kinetics 14.6 to 14.7. So reaction mechanisms. This is going to be the sequence of events that describes the actual process by which reactants become products. So we're looking at the steps that are happening in order to get us our final products in a reaction. So reactions can occur all at once or through several discrete steps. With reaction mechanisms, the molecularity of a process is going to tell us how many molecules are actually involved in the process. So, if we look up here where it says unimolecular means that there's only one elementary reaction. And my rate law, I find my rate law just by looking at my reactant. And so my rate law is rate is equal to K, and it's A, which is first order. Okay. A bimolecular process is when we have two molecules of A that combine together to give us our products. So if I have two molecules of A combining, then that's going to tell me that this is a second order reaction. So my rate law would just be rate is equal to K, A squared. Okay, and again, I'm getting this squared because I'm using two A's to combine. Okay, in a multi-step process, one of the steps will be slower than all the others. So the overall reaction cannot occur faster than this slowest rate determining step. And this is very important. I got to figure out what the rate determining step is. Okay, so here in this example, they're using cars to talk about rate determining steps. Okay, and I'm going to go ahead and explain this using the cars, and then I'm going to explain this using like your lunch line, okay, at school. So let's say that in order to get from point 1 to point 3, okay, I have to pass through Plaza A and Plaza B. Okay, Plaza A is really slow. The lights take forever to change, and so it takes people a very long time to get through Plaza A. Once they get through Plaza A, though, they're gonna get through Plaza B really quickly. So what we would say our rate determining step is our slowest step, which would be Plaza A. Okay. Now let's say it's the other way around. Let's say Plaza A is very quick to get through. Everybody gets through. The lights change really, really fast, and Plaza B is the slow one. So what's going to determine how quickly we get to point 3 is Plaza B. So Plaza B would be considered our rate determining step. Okay. Now overall, in both of these examples, we're getting from point 1 to point 3. In other words, it's just like a reaction. I have my reactants, and they're going to give me products. Okay, but it's going to take us a few steps in order to get there. Okay, so we're going to look at slow initial steps. Now, this is a reaction that we're looking at. Okay, and in this reaction, the rate law has been found to be this right here. So our rate is equal to K, concentration of nitrogen dioxide, and its second order. Now, the carbon monoxide is necessary for the reaction to happen, so I need it in order to actually get these products. But the rate of the action doesn't depend on its concentration, so I can double carbon monoxide, I can triple it, I can quadruple it, rate won't change. Okay, so in other words, it's zero order with respect to carbon monoxide, which is why I don't have it here in my rate law. So what this is saying here is, since this is second order, it's telling us that this reaction is probably going to happen in 2 steps. Okay, why? Because we just said that I cannot have termolecular reactions. Those are really, really rare. Okay, so this is a proposed mechanism for this reaction. Now again, it's not saying that this is exactly what happens, but this is something that makes sense. These are some steps that could happen, okay? So in step 1, we'll have 2 molecules of the nitrogen dioxide combining to form nitrogen trioxide and nitrogen monoxide, okay? Now if I look back at what my actual reaction was, my actual reaction says nothing about these guys right here, okay? But again, these are proposed steps that happen in order to get us from point A to point B, in order to get our reactants to give us our products, okay? So there's our first step, and we're going to say that this one is our slow step, okay? Now, step 2, we've got nitrogen trioxide combining with carbon monoxide to give us our products that we actually see in that original equation. And this is a fast step. So NO3, I don't see NO3 in my original equation, which was on the last slide. So we're going to consider NO3 an intermediate. Well, if I were to actually like read this going across, NO3 is an intermediate, right? Intermediate means in the middle, and it is in the middle. So I'm going from this plus this is giving me this, and then this is giving me this. So nitrogen trioxide is in the middle, which is considered an intermediate, okay? So it's being created in the first step and it's being consumed in the second step. And then we said carbon monoxide here in the second step, it's not involved in the rate determining step, which means it doesn't appear in the rate law. So an easy way to figure out my rate law, and I'm just going to give you the shortcut right now. In order to figure out the rate law, I'm going to go ahead and do something really, really easy. So I'm going to look at wherever my slow step is. And since we said that our slow step is the first step, that's all I'm going to care about. Anything that is from the slow step above, okay? And I'm going to go ahead and look at those reactants. And let me go ahead and circle these so we can see them. So I'm going to look at the reactants, and using my reactants, I'm going to go ahead and figure out my rate law. And what did we say? We said that the rate law was rate, and I'm sorry my writing doesn't look so beautiful, is equal to K, and then we said that it's NO2 squared, okay, or second order. Okay, but again, all I did was I cared about the slow step and anything above the slow step, and I'm going to use reactants to determine my rate law. Now let's look at an example where we have a fast initial step. So here we have another reaction. Okay, here's our reaction, and the rate law for this reaction is found experimentally to be rate is equal to K, with nitrogen monoxide being second order and bromine being first order. Okay, now again, rate laws are experimentally determined, okay, and I can't look at my full molecular equation and figure out my rate law, but I can use elementary steps to determine my rate law. Okay, now since I have since the overall order is 3, we just said termolecular is rare. Okay, so then again, this rate law suggests a 2-step mechanism. Okay, so here we have a proposed mechanism, and it involves 2 steps. Our first step is that nitrogen monoxide combines with bromine to give us NOBr2. And our second step is that NOBr2 plus nitrogen monoxide gives us 2-NOBr. Okay, now we're going to say that the second step is a slow step. And we're saying that because, again, it can't be a termolecular process, so we got to have at least 2 steps involved. And I need to find a way to get that rate law that we had originally. Okay, now something different that we haven't seen yet, and we're going to start talking about next week, are these arrows that are going in both directions. So I've got them going in this direction and I've got them going in this direction. And this is considered equilibrium. Now, with our steps, remember we said that there's a shortcut that we can use. And so our shortcut, again, is I'm going to go ahead and care about wherever the slow step is. So my slow step is down here, and I'm going to care about only the reactants, okay? Now, if I have something on both sides of the arrow, such as in this case here, I can go ahead and cancel those out. So I'll cancel out the NOBr2, and all I'm going to use are my reactants. That's all we have left, and so I come out with my rate law being rate is equal to K NO second order and BR first order. And that's the rate law that was experimentally determined and we saw on one of the previous slides.